it's cleaned. Okay, so
Yeah,
you
cool.
can work.
Cool. Okay, so let's get started. Very most important thing you will hear today, all the files you need for making the workshop work, they are on Discord. So there's a zip file on Discord. Download that one because otherwise it's gonna be really tricky to follow along. Yeah, let me also download the same file. Uh, yeah, and here yeah, I'll open this in documents. Here the Conda environment is managed through the WSL. So this is the Windows subsystem for Linux. So we will have to do some tricks to access our files, but in principle on the computers here, the environment should be set up. For those who are at home, I posted some instructions on how to build that environment. It should work out of the box, but you may have to be a little bit patient because it needs to grab a bunch of packages, and depending on your internet connection, it can really take a while to have all of these. Okay, so let's open up the WSL. So I'm gonna type in here WSL. You see the little Linux penguin there, and that should give you a Linux terminal, and Ubuntu shell. Um, okay, cool. That seems to work. So now what we need to do is somehow point it to this folder that we downloaded. And this is already the first tricky thing. So within the WSL, if you want to access, let's say, your Windows drive, you have to go to this mount folder. So you can see here how I type it in, current directory /mnt/c. And that's the C drive of this computer. And in there, then the way the file system is organized is exactly the same as in Windows. So most likely what I'll now have to do is have a look inside of users, student, or something like this. Let's have a look. What's in there? Yeah, users. Yeah, which user am I? Student, I think. And now let's see if I have it in my documents. Permission denied. So I guess I'm a different account. Yeah, let's have a look here. Oh, yeah, I see. Sorry, I am teacher, but probably you are student. So in your case, the user will be called student. In my case, the user is called teacher. Okay, I see. Yeah. Okay, let's do it this way. And now documents. Yeah, and now I can see those files in there. Um, and I see here 9add underscore qsar.zip. So you can unzip that on the Windows side, but yeah, I'll try to do it on here. I don't know if the unzip tool is installed or not. Yeah, it seems to work. So now I can go to that folder and let's see. Yeah, all that stuff. All that stuff is in there. Um, yeah. Yeah, try to navigate there. Make sure all that stuff is unzipped, and then we can activate the environment and open up the notebooks.
Yeah.
Mhm. Oh yeah, the whole terminal, you mean? Yeah, definitely. Although the size of the text is, well, maybe I can zoom like this. Okay, yeah. Yeah, so if anyone has any struggles navigating to the right folder, please let me know and I'll be happy to troubleshoot. Okay, so now let's activate the Conda environment. So currently you can see we are here in the base environment and there is a special Conda environment for this session. It's going to be called something like 9add or 9add QSAR. I don't know exactly which one, so I will try something. Let's see if it will work. Conda activate 9add QSAR. Maybe it will work. Yeah, it could not find this environment, so let's list what we have installed like this. And oh, okay. Actually, it turns out that the environment is not installed on this computer. It's only installed on your computers. Okay, so that's great. So you have a lot of time to activate your own environment because I will have to install it here. So let's do that. So I'm gonna create a new Conda environment. I'll call it 9ADD QSAR, and I'll grab it from Conda Forge, and I'll specify that it should be Python 3.12. Let's begin with doing that. Yeah, and it's Conda, so sometimes it can be quite slow as it resolves various dependency problems. Yeah, and I'll have a look here how to build that environment, what I'll put in there. Okay, so the environment is solved. I will proceed. Okay. Okay, so now I have a fresh Python environment. I'm gonna activate it and install some software in there. Conda activate 9ADD QSAR. And yeah, I'm gonna install basically everything in there at once with pip because it's a little bit faster. And yeah, and what we have on there is enough and there are no conflicts. So let's try this. 2.2, I guess. 0.0 light GBM. I'm gonna put in there Node-RED, DQDM, and SciPy, scikit, learn, and pandas, numpy, shep, and Jupyter Lab. Okay, let's see if that will work or if I made any typos because it somehow, yeah, it looks okay.
Now.
So pip seems to be quite slow on this device, so thank you for your patience. I'll just have to wait until it installs, or maybe I'll kill it and install it through Conda. But usually Conda is even slower than pip, so let's wait. Let's wait for it. Okay, so while waiting for the first environment to install, I'm building a second one so that at least one of the two will work. Just a simple RDKit environment. So let's see if Conda can solve it better than the broken pip here. Because anyway, to start with, I'll have to show around a bit how does JupyterLab work? How does RDKit work? How do certain basic Python things work? How do you deal with molecules in Python? Basically, absolute basics. Okay, so as it's taking endless time to install those environments, I am going to parasitize upon someone else's environment, and I see the de novo environment. It works nicely here. It has JupyterLab installed. So for demonstration, I'll use this one. But again, your local environment, it should just straight up work. So now I'm starting a Jupyter server, which I simply run by typing Jupyter space lab in the command line here. Because this is a WSL, it's not automatically going to launch in the browser, so there's going to be a link here. You can copy that link and open it in your favorite browser. So let me try to open this here in Chrome, and let's see if that will work. Yeah. So now I have a notebook. I have a notebook available here. Yeah, great. So it means that while these environments are building, I can at least demonstrate some stuff. Cool. Okay, so let's start a new notebook, and we can basically pick which kernel to use. So let's use this one, and let's see if this thing has RDKit installed. So yeah, let's try this here. Yeah, it's importing, and great news, it does have RDKit installed. Okay, cool. So who in this room is familiar with RDKit? Can you raise your hand if you're familiar with ArcGIS? Okay, great. So it seems not everyone, but many people are familiar with ArcGIS. So for those who don't yet know it or don't yet know it so well, let me briefly describe to you what it is. So it's a Python library that does basically almost anything you want to do with molecules. It's a cheminformatics package, so it offers a nice way to parse molecules, read smiles, turn them into graph-like objects, and do all kinds of things with them, like generating conformations, calculating fingerprints, calculating other properties, managing them in whatever way that you want. So what's the way that's usually done? One typical way to insert a molecule uh, into ArcGIS, so this means to turn it into an ArcGIS mol object, is by providing it as smiles. So that's a line notation for a molecule. Monday it was explained, so let me give you an example of this. Let's pick a molecule. Let's draw the smiles for let's say amphetamine. So let's say I'm gonna do here mol equals, and then here I use this method from chem mol from smiles, and I provide the smile string in there. And for amphetamine, that's gonna be first there is a benzene ring, so aromatic carbon, ring opening, 5 more aromatic carbons, and ring closing. Then there is the aliphatic part, so that's uppercase. In there, there's a branching, and here I put my amine in there. And now inside of this mol thing here, I should have an ArcGIS mol object. Yeah, let's have a look if I can display this. Um, it somehow got stuck with this. That's a little bit strange. Oh yeah, okay, yeah. So here it is. If I put display around that object, it's gonna draw me a nice picture of that molecule. And of course, if I change up the smiles, let's say I wanna decorate my ring a little bit. So let's say I add I add a second ring on there. I can do that like this. So I open another ring, I close another ring. Yeah, and now we have this nice benzodioxole on there. Um, that's the simplest way to get a molecule into a liquid. In practice, if you have large data sets, you will store them in a few common formats. Can be CSV with smiles in there, or it can be an SDF with mol blocks in there. And these mol blocks basically give the connectivity and allow you to give all kinds of both atomic properties as well as molecular properties. Like for example, if you have 3D coordinates, you can provide those in there. If you have some custom properties, you can provide them. You can provide them as fields in there. Okay, let's have a look how my environments are doing. Oh, cool! Actually, it seems like it installed. Uh, Great news. So it silently did that. So let me switch to the proper notebook then. Um, yeah, awesome. So I'm gonna conda activate 9ADD QSAR, and then finally I should have an environment with all that stuff installed in there. Now I'm currently also already in the right folder, so I should be able to run all these notebooks. Now, first before I do that, let me kill this notebook here, in case it's gonna open the Jupyter on the same port. So now I kill that, and I will activate a new Jupyter server here, and let's see if that works. Yeah, it did. And let me copy that link here. And yeah, so you can see I killed the server, so I have server connection error. And now if I put in the new link, yeah, okay. So, and you can see here as well that the notebooks are here. So let's basically this workshop has 2 parts. The first part is we are going to do something like as simple as possible virtual screen. So I provided some bioactivity data, and we will build basically a simple QSAR model to classify actives versus non-actives, and then apply it on a larger data set and kind of intuitively judge is it fishing out like nice actives or not? That is particularly one to pay attention to because I think it's going to be quite directly useful for tomorrow's challenge. The second thing is a little bit more systematic and broad. Well, it's called here ADME screen, but it's basically I'm predicting blood-brain barrier penetration using various different methods and comparing them with each other. So random forest, gradient boosted trees, rich models, chemprop models, various descriptors, and so on. But let's first begin with the basic case. Yeah, so I'll open up this one here, and actually, this notebook, in principle, it should straight up run like that. There is more or less nothing needed there. But maybe let's say for didactic reasons, let's construct this from the ground up, and I'll comment a little bit what I'm doing as I'm constructing it. So I'm gonna make a new notebook. Yeah. Okay, sure. Like this? Is it better? Yeah. Yeah, you are far off. Sorry. Yeah, and maybe I could remove this. Yeah, okay. Yeah, so there's a little bit more space. Okay, so we will construct it from the ground up. So let's begin with loading our data. And for loading our data, we are gonna use pandas. So we import it as follows: import pandas as PD, and now this will allow us to open up the CSVs that we have in the data folder. So let's see if that works. We use the read CSV function for that. And then we provide the path, which is going to be something like data slash, yeah, drd3 actives.isn. So this is a space separated file with some molecules that are active at the dopamine 3 receptor. And I remember that it's a space separated file, not a comma separated file, so I have to provide a delimiter. And I'm gonna call this data frame actives. So let's see if that works. And that worked. And let's see what's in there. Yeah. So so you can see first you have the smiles, then you have some ID number, then you have the assay type, then you have what the measured value was, you have the units, you have the target, and so on. Actually, as it happens to be, we know that they are actives, so we are only interested in the smiles. That's all we want to grab there. Also, what you can see is that this file doesn't have a header. So we can provide here that the header equals none. Yeah, and now if we reload it, you can see now the headers they just became numbered. Okay, so we can do the same thing for the inactives now. And I'll just copy paste this line and turn this into inactives like this. And also go to the file with the inactives in there, and that should be oh, I cannot find the file, so maybe it's called decoys, actually. Now I remember. Yeah, so it's a subtle difference, but in principle, a decoy is assumed to be inactive. It's not known to be inactive. That's why they're called decoys, not inactives. But they are property match. Okay, let's see what's in there. If that has the same form. Yeah, so here in this case, of course, there is nothing measured. There are no assays measured, so we have just two lines. The ID of the molecule, as well as the smiles. Also, what you see in here, we have 34,000 inactives, so we have an imbalanced data set. Of course, we have much more inactives than we have actives, because to be active is a bit of an unusual situation. Okay, now we should convert all of these into RDKit molecules. So we just grab the column, we iterate through it, and we use the RDKit machinery for that. So let's import RDKit and let's do that. So like before, from RDKit, we import chem, and now we can do list comprehension to do this. So let's call this moles for molecules, actives, and let's write that. So for every smiles in there, we are going to do chem.mol from smiles of the smiles, for smiles in every smiles that's in the first column, like this. Now, because these are 2000 molecules, it may take some time to parse them. Well, this will be quite fast, but those 35,000, maybe it will take some seconds. So for this reason, I'm gonna add a progress bar in there so that I can see how long it will take. So I'm gonna import tqdm for getting this progress bar. And I'm just gonna wrap this TQDM around the array I am iterating through. TQDM dot TQDM. Okay, let's see if this works. Yeah, so it works, and actually it's quite fast. So now that it works, let's do it also on the inactives. And we just have to change these two things here. Yeah, and as you can see, yeah, even the inactives, it's quite fast. It takes just 10 seconds. Okay, so this is great. Now we have our molecules in our Dkit native representation. Now, if we would want to do a bit of machine learning with this, we need two things. The first thing is our endpoints, and the second thing is our features. The endpoints is very easy because we know we have a certain amount of actives and we know we have a certain amount of inactives. So this is just going to be a long array with 2,000 ones in there and 35,000 zeros in there. So let's construct that. Y equals, and let's say the positive category we will call 1, or maybe doesn't have to be a string. We will call it 1. It occurs however long is mole actives, and then we append to this 0 times the amount of inactives that we have, like this. Oh yeah, moles it should be. Okay. Yeah, like this. And now actually you'll see this Y is just like a huge array filled with a bunch of ones and zeros. Okay, so now already actually we have an endpoint. That was very easy, but our features is a little bit more tricky. So we should calculate some kind of fingerprint or some kind of other descriptors. And I know for this task, Morgan fingerprints work extremely well. So let's calculate those. So how shall we calculate molecular fingerprint? Again, we use some RDKit machinery for it that we have to import. So from RDKit chem, I'm gonna import the RD fingerprint generator like this. RD fingerprint generator. And now I'm gonna instantiate a fingerprint generator object for Morgan fingerprints. And I'll call it MFP gen, or M standing for Morgan. So that's from this fingerprint generator, I use get Morgan generator, something like this. Yeah, here. Also here already I can specify which settings I want to have. I know for this task actually it's not crucial, so let's use the most basic settings. So radius equals 2 and FP size equals 1024. I'm pretty sure that if you don't specify this, it's gonna pick these settings anyway. Now we can use this generator for calculating our fingerprints directly. So let's call this X because the convention is to put your features in an array called X. And again, we can do a list comprehension. So for every molecule in the both are actives and inactives. So let me concatenate this. We will calculate the fingerprint, and we use the MFP gen for it. MFP gen dot get fingerprint, and I'm gonna make it give the fingerprint as a NumPy array because the scikit-learn estimators we will use to train the models are expecting arrays of this type. Yeah, like this. Again, I'm gonna wrap this in a TQDM just so that we can see how long it will take. Shouldn't be so fast. Should be a few seconds, but still, just to be sure, let's put it there. Yeah, so effectively it's fast. It took 2 seconds. And actually now we have everything in hand already for training our first model. So now let's try that. And what we can do is let's build a LGBM classifier, so a light gradient boosting classifier. And the reason why we will use this one is because it happens to be very robust and it happens to be very fast. So we won't have to wait for 5 minutes while the model is fitting, even if your local computer may be a bit on the slower side. So let's import the LGBM classifier. So from lightgbm import, I think it's LGBM classifier, yeah, like this. Um, let's instantiate it. So I'll call this CLF, short for classifier. And I don't think we even need to change the basic settings. I'm just gonna make sure it will utilize all the cores, and I'm gonna make sure it's not verbose and it's not gonna print out too much stuff that I don't want to hear about. Now, before we fit our model, only one more thing is missing, and this is splitting up data. Because we want to calculate validation metrics, here in this case, it will be just on a basic random split, just to see more or less ballpark how well our models are performing. So let's make use of the sklearn machinery to split up the data. So I'm gonna import that from sklearn model selection, import train test split. Yeah. And yeah, and this is gonna I think this is the order, if I'm not mistaken. Actually, I'll need to have I should have a quick look here. Yeah, it's X first, Y second. Okay. Yeah, like this. Y test equals uh, train test split, and it's basically gonna shuffle around the data set for us and divide it into randomly into what's gonna be our external test and what we will be fitting our LGBM classifier to. So we give it X and Y, and then we should be giving it the ratio of what's in test and what's in train. How is this like called? Yeah, test size is called. Yeah, and let's look it to be deterministic here. Yeah. Okay. And now finally we can fit. And fitting, it's the most easy part. So we have our classifier object and we do clf.fit. We fit it on our train data, so X train and Y train. And now we wait. As you can see, LGBM is fast, so we wait literally for a second. Now we want to see how good our model is. And our model is it's expected. I would say it's expected to be good. But okay, yeah. Let's see. It's a classification model, so we should think of some good classification metrics. Most typical for classification problem is AUC or Matthews correlation coefficient. So let's begin with Matthews correlation coefficient. So let's import that from sklearn metrics. We can import Matthews correlation coefficient. And now what we do is we use our fitted model and predict we predict the labels. So we do that on X test. So that's the test split of our features, or the features from our test split rather, and we are gonna call this Y predicted. We know what it should be, and that's the values that are in Y test. So now we can print, let's say, MCC equals, and then we calculate this value here. So, and we compare Y test with Y pred. And yeah, so it turns out our model performs well, perhaps even suspiciously well, because MCC is basically bounded between 0 and 1, or yeah, it's bounded between 0 and 1, 1 being basically a perfect correlation. So it means that apparently our task is quite easy. Our actives are really distinct from our inactives. So let's see if the other metrics also trail this. So let's try to calculate the AUC. So I'll import the ROC AUC score. And I'll print out that one. Now, for this, actually, we need prediction probabilities. Because with this Prediction function, we just get the labels, 1 or 0, active or inactive. But if you want to see how well we are ranking and ordering our compounds to see, for example, if we have something like early enrichment, which is very important in virtual screening, we need those probabilities so that we can rank them. So let's get those probabilities. And again, it's very easy to get them. Instead of predict, we just do predict underscore proba for probability. And yeah, and now let's calculate our AUC. So I'll copy paste that here. And yeah, now here instead we should put the probabilities. Now here there is something which is a little bit tricky. This output, it will contain the probabilities for all classes, and we are interested in the positive class. So let's slice that in such a way that we only get that one like this. And now it should give us the AUC. So let's try. Yeah, and so here again, we can see that actually this AUC it hits the theoretical limit. In other words, our classification problem is probably too easy, or our classifier is very, very powerful. Now, we have a fitted model in hand, so now we can do something with it. And what I suggest to do with it is I have in the data folder a list of smiles of 125,000 commercially available compounds. We can screen those, and then we can have a look. Do those compounds, do they look interesting? Do they look like dopamine 3 binders, or do they just look like random molecules that are false positives? So let's get these molecules into our dikit. So again, we will use pandas for it. So I'm going to call this df zinc because this database is called zinc. It's just a subset of zinc. And yeah, I'm going to use pandas for this. So read CSV. And it's data slash, yeah, zinc 125K because it's 125,000 of them. And yeah, I am not sure what is the separator in this file. So let's have a look. Yeah, it's apparently space separated as well. So let's put the delimiter to space like this. Yeah. And yeah, so you have basically the smiles in there, and then you have the internal code inside of the Zinc database. Again, at the moment, we are just interested in the smiles. So let's just grab those smiles. And let's turn them into molecules. So we can call it zinc moles, and we do it in exactly the same way. Mole from smiles for every smiles that's inside of that column. df zinc smiles like this. Okay. Yeah, and this definitely we are gonna make a progress bar again because 125,000 molecules, this will take a little bit of time. Yeah. Okay. It's loading them. And now before we put those into our model, we need only one more thing, and this is converting them into fingerprints. So and with the molecules, of course, it's easy. So let's call this zinc FPS. And yeah, we can even copy paste what we have up here and just change the name of the array that we are iterating through. So this thing here, we just changed to zinc moles. Let's see, zinc moles. And yeah, so let's generate them. Yeah, it's faster to generate the fingerprints than it is to read in the molecules because it doesn't have to do any sanitization or anything like this. So it's like super fast algorithm. Okay, so we have our fingerprints. We can use our model. So let's predict the probabilities, and let's put those 125,000 molecules in there. Yeah, so let's call this zinc proba, and let's see how long that takes. Yeah, so it's very fast. It takes something like half a second, and now we have the probability of being active for every single compound in there. So now let's find the most active compounds, and what we can use for that is some NumPy sorting to get the let's say argument that corresponds to the highest value. So let's yeah, import NumPy as NP, and now we can do NP arg sort, so argument sort, zinc probabilities. And again, we are interested in the positive class. So we slice it like this. And here in this case, it's gonna sort from low to high, but we want to have it sorted from high to low. So we can make the array backwards. And let's say we are interested maybe in the, let's say in the best 10. So let's do it that way. So let's take just the first 10 in this line. Let's see if that works. Yeah, so now we have 10 IDs. So now let's have a look at those molecules. So let's iterate through them and let's display them. So from the zinc moles array, we get our best molecules. And then let's kind of intuitively judge what we think of those molecules. Okay, so here they are. Here are the best molecules. And let's say those who are familiar with aminergic GPCRs, they will immediately say, okay, there is very typical, recognizable common motif in there. And that common motif is piperazines, including N-aryl piperazines. Also, what is very typical for these D2, D3, and so on binders is on one side they have piperazine, then they have a long flexible tail in the middle, and then they have some aromatic thing dangling on the other side. For example, this molecule I'm circling here with my cursor, that's an example of such a molecule. But otherwise, yeah, you can see all these typical motifs are here. Yeah, actually, even here, there's isoquinoline. That's another one of these like typical typical common motifs. I would say, looking at these best 10 molecules, I would say our model learned something very shallow. It learned some very kind of like straightforward substructural patterns of what happens to be active and what happens to be measured at the D3 receptor, but well, it works and it gives optimal metrics. So that's the short virtual screen. Okay, so here now I basically built it on the spot, so it's a little bit messy, but here in this other notebook called virtual screen underscore LGBM, I do exactly the same thing. So basically what I was just describing, it's all in there except a little bit cleaned away, and there are a little bit extra uh, metrics on there. So let me run those cells and just a little bit comment on it. So yeah, here for example, I add one extra function in there, and this function is the enrichment vector. And in a virtual screening setting, this is actually a very informative metric because if we are virtual screening, typically we'll have a look at millions of molecules and we are interested in maybe the best 100 or the best 200 because we can buy those and the rest we will not buy and we will not test them. So we don't care if we are classifying inactives correctly or if you are having some false negatives. We just care about the fact that in the 150 whatever molecules that we consider the best, that there are as many hits as possible. And the way to quantify this is through the enrichment factor, which is the ratio of the percentage of hits in the subset from screening versus the hit rate in the total set. Yeah, and I just wrote a little function for that. Now here you can see we are loading up that stuff in exactly the same way. Maybe I named the variables in a little bit different way, but it's exactly the same thing. It's just all inside of this one cell. Yeah, here there are no progress bars, so we will just have to wait for a few seconds and hope that it will finish. But so it already finished, so that's not so bad. And again, here we use this light GBM classifier. Actually, in principle, this task it could work with almost any other classifier. One thing you just have to consider is that we have a relatively large data set. So we have something like 40,000 molecules or 37,000 molecules, and already at this size, some estimators like random forest, they will be like a little bit slower. Maybe you'll have to wait for a few minutes or something like this. Whereas this light GBM, it's really well optimized and it tends to find a good solution in a short time. Okay, so let's run this one here, and yeah, you can see that the metrics they follow what we had before. Here they're just rounded up, and also our extra metric that we introduced the enrichment factor at 1%, you can see it's 17-fold. And that's actually the theoretical maximum you can have at this 1%. So in other words, we can say for virtual screening purpose, this is a model that at least within its domain works very, very well. Now, the whole time I'm commenting like, yeah, maybe the task it's a little bit too easy. Because the metrics are so good. So I inserted here a baseline method. And this is a KNN with k equals 1. So basically, it looks for the most similar compound in the dataset, and it just takes the label from that one. So it's like strict similarity-based classification. It's not pooling various neighbors. It's really just only using the closest neighbor. This one actually, it takes a little bit, it takes somewhat longer, although here also it completed quite fast. And you can see the metrics are still like very, very good. If you compare them with the LGBM ones, they're slightly worse, but really not that much worse. So this further confirms, yes, it's really a very easy classification task. This is in part why nowadays people are saying when you are training QSAR models, when you are developing new methods, DUD, which is where these molecules come from, is not a good set to do it because the tasks actually are too easy. One more way to show that the tasks are really easy is by reducing information in our fingerprint. So currently, we have a radius of 2 in our Morgan fingerprint. So we have all these nice circular environments in there. Now imagine I put the radius to 0. And in that case, actually, we will only have atomic information. We will not have any kind of connectivity information. So we can have a look how much our performance is going to deteriorate when we do this. And in case the models are still too good, it's another sign that the task is really on the easy side. Yeah, so here we can see actually the MCC, it very slightly deteriorated, but it's still like working very well. So like most likely what this means is that there are some underlying things about our active data that's making it too easy for the model to find these compounds. And actually, if you think about it, it makes sense because you could say if you build a mental model of what's a D3 binder, you could say basic amine, some aromatic rings, and all those things you can actually express as strictly atomic features. So this is in part why this task is so easy. Okay, so let's return to normal size fingerprints so that we can keep on going through this notebook. Yeah, it's gonna take a second. Yeah, and so here again, we do the same thing. We load up those zinc smiles. Here in this case, I'm adding the name of the molecules as a property, just so that I can display them in a little bit cleaner way afterwards. And then again, I'll put them here in the already trained classifier model, predict their probabilities, rank them from most probable to least probable, and display the best 10 or 20 or something like this. Yeah, in this case, actually, I have the best 20 display there. So let's have a look here. Yeah, and here also now I'm rendering them as a grid. So it's a little bit nicer way to see them all at the same time. And actually, you can recognize in here basically the same molecules as we had before. So we had different random seeds and so on, but it's robust enough that it's still like ranking everything in this zinc dataset the same because it's just like finding and recognizing those piperazines in there. Cool. So for this notebook, for the first out of two notebooks, conclusion is clear. The virtual screen gives some nice molecules. The classic motif is in there, but well, the task is a little bit too easy because even a KNN works there. So now let's switch to something a little bit more tricky, and that's AutoMap properties. And for this, I have a set with about 1,000 molecules in there, and they have a label. Do they penetrate the blood-brain barrier or not? Which, of course, is a very important property of molecules because in some cases, it's extremely important that it does. For example, if you're making antidepressant or something like this, you don't want it to be strictly peripheral. In some cases, it's absolutely necessary that it doesn't cross the blood-brain barrier. For example, when you are making next-gen antihistamines and you don't want people to get drowsy because of actions at CNS, various CNS receptors. Very useful UDMAP property. Yeah, we can even have a look inside here, how that file looks. Yeah, so they're even in there with their names. So most of these are uh, marketed drugs, and yeah, and the smiles is provided here in a column called smiles. So um, let's go through this notebook line by line. So a lot of this is the same as what we did before, but we have some additional things in there. For example, you can see here we are importing the descriptors module of RDKit. And these calculate all these like continuous descriptors, graph theoretical descriptors, a few fragment-based descriptors, and so on. In total, it's a list of 200 or so. And in practice, some of them tend to correlate quite well with ADMET properties. For example, calculated log P tends to quite cleanly correlate with that, but even things like molecular weight tend to be affected there. Then to have even a few more descriptors, I'm importing this package called Mordred. And Mordred is conceptually quite similar to the way descriptors are calculated in RDKit. They just have a bit more of them and slightly different ones. So sometimes Mordred is better, sometimes descriptors, RDKit descriptors are better. Yeah, what else is there? Okay, so because I didn't want to manage with any annoying CUDA or NVIDIA stuff, I force the CPU on here just to make sure we don't have to troubleshoot that. And then after that, I import ChemProp. So this morning I was talking about GNNs and their great performance in some open benchmarks. So for this reason, we want to have a look. Will GNNs also work well for this task? Of course, the GNNs will not be so hyper optimized as they were in the case of the Open AdMet challenge. Yeah, and then here, basically, again, we open the data frame and we get the property of interest and we get the molecules. So let's run that and let's see if everything cleanly imports and if it was all installed properly. Uh, hopefully, hopefully it was. Yeah, usually the first time importing ChemProp can take some time. Sometimes even it has to download some pre-trained weights. Okay, that's done. All our stuff is imported. And now, again, we load up our data and we split it up. Again, I'm picking here a random split, which sometimes makes the task a little bit too easy, but I think for illustrative reasons, it's fine enough to do it this way. Another thing is that something like a scaffold split in ADMET properties, this is a little bit less relevant than in predicting bioactivity. So what's happening here? We are splitting X and Y. Here in this case, I'm actually using initials for that so that I can share the same splits across different feature types. And we calculate 3 different feature types. The first type is RDKit descriptors, the second type is Mordred descriptors, and the third type is Morgan fingerprints, the same ones as we were using for our LGBM virtual screen. So let's run this and let's see how long that takes. Um, yeah, so RDKit descriptors are quite fast. Mordred should be a little bit slower. Yeah, that's gonna take a few minutes. So let's wait for that. Yeah, and then once these are built, what we will do is we will try a few classic approaches and classic models and actually see how they compare with each other. For example, often it's said that which exact tree-based model you use, whether it's XGBoost or LGBM or CutBoost or AdaBoost or Random Forest or whatever else you can think of, it's often on par with each other, but still in practice, sometimes one tends to be better than the other. Also, it depends on which hyperparameters you pick. Yeah, so you can see it's completed. It's completed here. So actually, maybe before we build those models, maybe let's have a look what's inside of these arrays, um, just to make this a little bit more concrete. For example, on here, I think this dictionary should be containing all the names of the descriptors that are in there. Yeah. Okay. Yeah. So you can see here, actually, that's the list of all the Ardiki descriptors. So uh, you have quite a diversity of things in there. Some of them, like let's say, uh, rather easy to interpret, like the molecular weight or the amount of heavy atoms or the number of electrons or something like this. Some of them a little bit more difficult to imagine. Like, for example, there are some descriptors based on the burden matrix, and yeah, and a bunch of descriptors here that are based on partial charges and van der Waals radius, and some based on some cutoffs, making some kind of sum of those. So often the interpretation of these is kind of fuzzy. In case of the fingerprints, it's simple. So if we have a look at the first fingerprint, yeah, you'll just see it's a big list of zeros and ones. And it's actually mostly sparse. So if you'll have a look, the length is 1024, but the amount of ones is 99. So it's 90% unoccupied, which is information theoretically not perfectly efficient, but well, it does the job. Yeah, now in case of the moderate descriptors, um, here I just store the numbers, and you'll just see that there is some huge array here with a bunch of values in there. I think moderate should be something like 1600, yeah, 1610 values. Okay, so these are our features that we have. Now let's see what's the best model, what are the best features. Um, yeah, and so what's happening here is we try out three model types: an ordinary random forest, a light gradient boosting regressor, as opposed to the classifier we used before, and then as something like a baseline model, we use a linear model, we use ridge regression. So how can we use ridge regression and not some other linear model? It's because ridge regression is a little bit more tolerant of correlated descriptors. So the often where some other linear methods fail, this one can somehow deal with it. Okay, so let's run it and let's see. Because our data set is quite small, it's training pretty fast, and yeah, so you can see that it's already halfway. And what you also can see is that the metrics of these models, they are actually not so good. So R squared is around a half. Um, MAE is not all that good. And you can see that actually the very best model we have is like still kind of on the weaker side. Now, the this actually this makes sense because actually measuring blood-brain barrier penetration is tricky. It's known to have a lot of experimental noise. It's known that different laboratories don't agree with each other. So even if you would have perfect predictor, maybe your R squared at best, it can be something like 0.75 or something like this. Another thing is that the underlying factors that determine blood-brain barrier penetrations are a multitude of things. For example, some things cross the blood-brain barrier through active transport. Some of them do it through passive diffusion, and the things that determine whether that's going to be possible or not, they're completely unrelated to each other. Okay, so these finished training. So these classical models, they are very fast, and what turned out to be the best one apparently is an LGBM model with moderate descriptors. Actually, if we compare it with Morgan fingerprints, I would say it's quite a bit better. And that's something which is rather well known. When QSAR modeling admit properties, those descriptors, they somehow tend to perform a little bit better than fingerprints. In part because in fingerprints, for example, the size of your molecule, lipophilicity of your molecule, it's something that you cannot directly extract. For example, the Morgan fingerprint of um, octane and decane, it's the same thing because those bits, they will just overlap with each other, which means that if you have a property that depends on molecular weight or lipophilicity or something like this, you kind of like lose this information. And this is why the performance a little bit deteriorates there. Okay, so now let's move into the future, and let's see if we can do better with Camprop models. Now, before I explain what's happening here, I'm already gonna run this cell because it tends to take some time to train. In part also because I'm running this here on CPU. Also, I should specify beforehand that just to save training time, the amount of epochs in here is like a little bit on the lower side. I think that's here. So just 20 of them. In practice, if you would be running this in production, maybe you'll run a dozen more, or you'll do early stopping, and only when the performance degrades or doesn't increase for some time, you just stop the model where it is. Oh, actually,
There was that a huge number of epochs will actually produce an overfitted result.
yes, yes. Actually, in practice, anytime I've played around with Camprop, surprisingly, after a few dozen epochs, you usually already get most of your performance. And after that, if you want to prevent overfitting already, you need to take some care. So very often what may happen is that you do 200 epochs and then you look at the best checkpoint, and the best checkpoint was checkpoint 15 or something like this. Yeah, okay. So actually, I have two Camprop cells here. So what I just ran here, that's basically the vanilla Camprop. So this is a Camprop without any pre-initialization. It just for the atoms taking Morgan-like invariants, so atomic number, amount of neighbors, and so on, and it's doing message passing to get embeddings, and then it's using those embeddings in a FFN to predict the properties. Here, actually, I explicitly define quite a few things because Camprop is quite sensitive for it. So here you can see I'm using the standard featureizer. So that's with this, I actually choose that as my atomic properties. I use these ECFP-like properties. Also, what I do is I scale my targets because, again, Camprop is a little bit sensitive to that. So often you need to transform your data so that, for example, you transform it into Z values or something like this, because if they are too large, or if they are too broad, somehow it can lead to performance deterioration. You can see here the FFN, the feed-forward neural network. It's pretty shallow. It has 2 layers, 300 hidden dimensions. So this is a rather simple setup. Yeah, then all these things I define, like how the MPNN works, what FFN I use. I put that into the trainer here. I get my data loaders because let's say Camprop is modern, so it takes its data through these more flexible data loaders. So you kind of have to reconstruct this data so that it can read that in the way that it likes, and it actually also makes it possible, for example, to use these APIs to get data from directly from a source like Polaris, for example. Yeah, here another parameter that's very important in Camprop is the learning rate. And one of the reasons why often the performance deteriorates really rapidly is because the learning rate is set a little bit too high. Okay, but let's have a look. Let's have a look at the numbers. So this non-pre-trained model, what kind of numbers do we get? Yeah, so we can see here the R squared actually it's quite bad. It's not even better than our rich models. So and this is probably because our data set is a little bit on the small side. So what we can do in Camprop is like leverage the pre-trained models or foundation-like models that already were trained on millions of molecules. And the one that we would like to use here is Chameleon. So how does Chameleon work? They train gigantic Camprop model to predict 1,600 Mordred descriptors. And actually, these happen to be extremely informative. And the MPNN that results from this and the embeddings that result from this, somehow they capture some kind of chemical relations between molecules. And the idea is if we pre-initialize our MPNN with those weights, maybe we will get a little bit better. We will get a little bit better performance. So let's run this cell here, and yeah, this one is definitely gonna take a while. And the one of the reasons for that is that just the amount of parameters is uh, kind of gigantic. So this one here, yeah, certainly I'll have to wait for a minute or five. Actually, while this is running, let me show you some other thing, and we can return to it. We can return to it when it's finished. And that other thing is the probing the models for explainability. So I'm just gonna take the same notebook and I'm gonna duplicate it so that I can run two instances of it. So let me import the same molecules, calculate the same descriptors, and build the same models, and then we can probe them. Yeah. So let's do that here. Yeah, and then that one there. Yeah, and how long did that take? Let's have a look here. Yeah, that took something like a minute, so that's not so bad. Okay, so and let me explain to you what I'm about to show to you. So basically, we are going to use the SHEP package to try to explain individual predictions. So what we want to do is within the molecule visualize where are the predictions coming from? Which atomic and molecular determinants are making the model say this is going to be blood-brain barrier penetrant or not? And the way we will do that is we will take a model that's trained on Morgan fingerprints, and then we will probe the predictions to see which of the bits in the fingerprint are relevant for the prediction. And when we know which of those bits are relevant and how they contribute, we can visualize on a molecule using these colored maps to see where this performance is coming from. So let's see how these, yeah, they are just starting to train. So let's wait for another minute. Yeah, most likely this is a little bit slow because there is competition between all the CPU cores that are doing the ChemProp here in the one notebook and ChemProp in the other notebook. Yeah, also here you can see that the original non-pre-trained ChemProp, it has 400,000 trainable parameters. If you go down here to Chameleon, you have 20 times more. You have 9.4 million tunable parameters. So, and actually that corresponds to more than 20 times slower training times. Um, cool. So, yeah, and I have to warn a little bit beforehand that this block where I'm doing this shape visualization, it's kind of messy code. For example, I'm calculating the fingerprints using the old API. And the reason why is that it's a little bit easier to get the bit information for it. So that's the reason why, yeah, you can see here I'm calculating them using Alchem method because to get this bit info is the most straightforward in this way. So it's like a little bit stupid to do it this way, or it looks a little bit improper, but yeah, it's easier to write it that way.
Are you getting the majority that?
Uh, oh, I I am not sure I'm not sure if I wrote it as majority bit or if it just takes the first one.
Yeah.
Yeah, I like because the thing is they are for individual predictions. So it means that when you have a majority bit within a molecule, it's like a very pure bit collision. And the typical context in which you would do majority voting is when you do, let's say you train a random forest and you get your feature importances, and it says, okay, bit number 100 is the most important one, and then you can look in all your molecules. What does bit number 100 tend to correspond for, and then you can do majority voting. But that's only like usually on the whole set level. This is like meaningful thing to do. In case this is on the single molecule level that this happens, actually what you can just do is make your fingerprint longer, and you will not have the collision. And you will have a more straightforward explanation. Okay, so in the meantime, these models finish training, so we can run this code book and we can have a look what the output looks like. So, yep.
For these models, we don't need to check if there is any outliers.
Well,
Cleaning.
in principle, one of course one should check it. Or like let's say if for example you build a regression model and the metrics look really bad, of course then you'll maybe first you'll visualize it and have a look and see if there are any particularly bad predictions that are making your metrics so bad. Then after that, you can do some more, let's say, systematic or statistically sound outlier detection. But in practice, if you are happy with your regression metrics, then the outliers, it's like that's an analysis you don't necessarily have to do. And the reason why is that when building QSAR models, it's really about this kind of like hands-off, data-driven correlation type of approach. Whereas usually when you want to remove outliers, it's more, you usually have some kind of like mechanistic reason for it, which here is something like we kind of assume the numbers kind of cancel each other out. And the fact that you may have a few outliers in your training set, or you may have a few like particularly bad predictions or something like this, that just like, well, every model has its limitation, and you can just take that as it is. But it may be that if you remove the outliers, if you clean up your data properly, you will get better regression metrics. Okay, so in the meantime, let's have a look at what Shep says here. And you can see here, basically, I picked two molecules, one very greasy one that can enter the brain quite efficiently, and then here one ultra polar one that well, actually, because it's a sugar, you can kind of discuss how well that will get into the brain. But here, actually, it's not about how accurate our prediction is. Here, it's about, according to Shep, what is the explanation that our model gives for why it made a prediction of this type. Yeah, the color coding here is red means increased blood barrier penetration. Green means decreased blood barrier penetration. So what's happening here on this map, it's kind of, yeah, this is kind of logical. Even if it's not true for the sugar, the more aliphatic alcohols that you will have in your molecule, the less likely, of course, it is that it will cross the blood-brain barrier. Likewise here, on this molecule, it's recognizing this kind of, again, this piperazine ring and these sort of like lipophilic elements that often are associated with this CNS penetrant lipophilic molecules. So all in all, you could say that the Shep analysis here is rather following intuition and rather in line with what we would think. And yeah.
Does this also convey like the size of the molecules? Does that also involve it influence the permeability, especially?
Yeah, so here in this specific case, no. Because we are probing it using Morgan bits. And actually, as we were trying to explain why our Morgan-based models don't work too well, actually the reason why is exactly this factor that you mentioned. But on the other hand, if you want to visualize the dependency on, for example, molecular size, anyway, with a color map, it would be like not so straightforward to do that. But it's true that actually if you would try to interpret the models based on descriptors, you will see that actually these size correlated, lipophilicity correlated descriptors, they are really like carrying most of the performance. Yep.
I'll ask, when you look at the glucose or whatever sugar it is, like why did the primary alcohol group actually, why is it like not very penetrating?
No, actually, green here means, yeah, sorry, the color coding is non-intuitive. Green here means the opposite. So green means less BBB penetrant.
Yeah, the primary one is red.
Oh yeah, sorry. Yeah, okay, yeah, like this one. Well, it may be that because it's using Morgan fingerprints that it's taking into account fragments that are centered on this alcohol, but that incorporate this sugar-like substructure. So it could be that it somehow figured out like, wait, actually, if it's a sugar, it needs to be adjusted. But of course, these are explanations of why the model chose to make its prediction. And actually, when you have a kind of like weak model with R squared of 0.5, like we have here, it may well be that, first of all, the predictions are completely wrong. Or second of all, the reasoning that leads towards correct predictions is also completely wrong. And basically, what we see here is just the reasoning that our fit had. Okay, let's have a look and let's see. Yeah, I think that Chemprop it's still training, so it's taking a super long time. But I would say with running the SHEP, we are basically finished here. So let's finish the session with any kind of like open questions you have or any troubles you ran into running parts of this notebook or any other follow-ups that you'd like to hear about or see. Yeah, and if there are no such question, in that case, I thank you. I thank you for your attention. Yes.
Those ones are running specific on CPU, or is the GPU available as false?
Yeah, it's like often Chemprop it can run almost as fast on CPU as GPU, but here somehow it tends to be really slow. But I deactivated GPU actually mainly so that it doesn't um, mess up with various different NVIDIA drivers, CUDA versions, and so on on all these devices here.
But if it's not critical use it like predictions and then it does
Yeah.
will really nice too. But I guess it's when it's
Yeah.
very big library.
Yeah. Okay. Actually, one more thing to say. The model just finished, and we can actually see the pre-trained Chemprop compared. So this is the non-trained. It had R squared of 0.3. The pre-trained one has R squared of 0.532. So actually, the pre-training it does contribute something. It's still not such a good value, but it's much better. Yeah. Okay, cool. So thank you to the online people as well. I'm gonna mute myself now and enjoy the rest of the conference.